Hey everyone! Today we will quickly go over the reflection and refraction lab packet. It's pretty straightforward today, so let's get started. In part 1 we will be studying the law of reflection. Here's the setup that we used. We have a light source on the left side. We have these slits just to help guide the light. Here we have a rotating table. And on the table there's a mirror. In short, light came from the light source, passed through the slits, reflected off of the mirror, and this allows you to study the angle of incidence and the angle of reflection. As you rotate the mirror, the incoming ray will reflect off at different angles. You can see this in the diagram on the right side. For instance, if the incoming ray was at 60 degrees here, it would come in, reflect off, and then exit, hopefully also at 60 degrees. You can also see this a little more clearly on the next page. You have the round rotating table. Of course, you have the mirror, which is lined up right here. The normal to the mirror has to be perpendicular, so that would be right here. We aim the light so that the light always bounces off the center of the mirror. The angle of incidence has to be measured from the normal. And the angle of reflection also has to be measured from the normal. Here's the data table for this part of the experiment. You will be tasked with taking measurements for every 10 degrees increment for the angle of incidence. The way the video actually works, you'll be starting at 90 degrees in trial 1, so right in the bottom middle. From there, you'll move on to 80 degrees, 70, etc., etc. When you get to 0, so when the incoming ray is lined up with the normal, you will take a measurement in the top middle spot, and you'll also record that measurement for trial 2. From there, you will keep increasing the angle of incidence until you get back to 90 degrees. Hopefully this makes more sense when you see the video. So here's the video. I'm going to fast forward to the relevant parts. We start by just explaining some of the physics that's going on. We point out the normal. In the video you can see the rotating disc around the outside. Here is the labeled mirror. We line up the mirror right with this center line, so that the normal will be what is currently this vertical line. The incident ray is coming from the left side, so the reflected ray will be shown on the right side. And right here we mentioned that you may need to pause the video for each measurement. I think that's a good idea. Rather than try to take all the measurements in real time, you should stop the video and take a careful measurement. Okay, so let's go forward a little bit. Okay, and this is where it starts. Let me actually go back and play here. Okay, so there's your very first measurement. The incoming ray is at a 90-degree angle of incidence. It quote unquote reflects off the center of this mirror, and you have an outgoing ray that has an angle of reflection, and this will also be about 90. Let me actually go back just a little bit. Okay, so that's the earliest time right here. So your incoming or your incident angle will be 90 degrees. And your outgoing ray actually has an angle of reflection. It looks to be about, I would say, 89 degrees. So we'll go back to our data table. And in the first spot, we will mark down 89 degrees. Our next measurement has to occur when the angle of incidence is 80 degrees. So we will go back to the video and play and wait till the light gets to 80. Okay, so I paused the video when the incoming ray is at 80 degrees. Notice that it's actually not exactly at 80 degrees. In case you're not aware, to step forward in a YouTube video, if you just want to step forward a very small amount, you can use the comma and the period symbols on the keyboard. So period will move it forward just a little bit. Right there looks to be at about the center. So now you have an angle of incidence of 80 degrees, and the angle of reflection is, I would say, 79 degrees there. I'm sorry, 81 degrees. So I will go back to the data table and write 81 degrees. The next measurement has an angle of incidence of 70 degrees. So we go back to the video, we let it play. We stop when it gets to 70. Let's say I go a little bit further. Okay, so I go a little bit too far. If I want to go back, I can use the comma key on the keyboard to step backwards. And then I just line it up right there. So I have an angle of incidence of 70 degrees. And I will let you record the angle of reflection here. Let's move forward. When the incoming ray gets to 0, right there, I will make a measurement in the top middle of my data table. So you can make your measurement right there. That measurement is going to be the same as the first measurement for trial 2. When we continue the video, it'll move on to the incoming ray, which is now the lower ray. This will be at 10 degrees, so then you're going to make the angle of reflection measurement right here, and that you will record in this second spot for trial 2. Okay, and then you just continue doing that until you get all the angles. After you've finished this table, you will move on to the next page where there's some questions that you have to answer. And then you'll start with part 2, the law of refraction. In part 2, we're going to test Snell's law, this angle of refraction law. The setup for the experiment is very similar. The only difference is that instead of a mirror on the center of that rotating disc, we have this prism. So now instead of reflecting off, when that ray comes in, it'll strike the center of the block of acrylic and it'll refract into the plastic and exit out the backside. The data table for that is below here. There's also a couple more questions you should answer. And here's the data table for part 2. The idea here is pretty much the same as in part 1 of the experiment. You'll start in the bottom middle of the table and work your way up until you get to the top. And then you'll switch over to the right side and work your way down. So let's switch to the video. At the beginning, they explain the law of refraction a little bit. In this part of the video, they show you the incoming ray on the left side. The ray strikes the center of the cylindrical lens. It refracts into the lens and it exits the backside of the lens. And then here you can also see a slight reflection off of the lens. For this part of the experiment, we can ignore that reflection. When we are dealing with refraction, there's two normals we have to consider. One is the normal that we use to measure the incident ray. And that would be this normal right here. You also have the normal that you use to measure the angle of the refracted ray, and that would be the normal coming out the back of the lens. So you have the incident ray coming in. It refracts at, well, the incident angle is shown right here. It refracts at the refracted angle right here. And again, this reflection you can ignore for this part of the experiment. At this point in the video, I would have already taken measurements for 90 degrees and 80 degrees. Right now I have a 70-degree angle of incidence shown. It refracts at, it appears to be about 39 degrees. So I'll go back to my data table. This would show up right here, 39-degree angle of refraction. And then you just continue on. After you have finished this data table, you have another question to answer down here. Note that your measurements are not necessarily going to be the same between trial 1 and trial 2. The differences for that I will leave up to you to decide down here. And then after you answer that question, you will have to make a graph. For this graph, you can again use Excel, or you can use the in-class program that we used last time. The x values for your graph have to be the sine of the refracted angle. So for instance, this 39 degrees I have. The x value for that would be sine 39 degrees. If you calculate that, you have to make sure that your calculator is in degree mode. So you should get a value of about 0.63. On the y-axis, you're going to want to use the sine of the incident angles. So you'll have to calculate the sine of each of these values in the table. If you're using Excel, I will show you a trick that you can use to help you plot this. Before I switch to Excel, let me just say that this very bottom row on the table, I'm actually going to cut that out of the lab packet that I give to you guys, because the 90-degree angle is sort of it's a pathological result that won't really help with our data. So ignore that bottom row and start taking your measurements at 80 degrees for part 2 of the experiment. Here I've pulled up an Excel spreadsheet. I have my first column will be the x values, the refracted angles. The second column, the y values, will be the incident angles. I've taken a few points of data from the table, starting with 80, then 70, 60, etc., etc. For the refracted angles, I've made up some values. So in the very first column, you'll be putting your own data. And note that all of the data that we're inputting here will be in degrees. Now the difficulty that we're going to have with Excel is that if we use the sine function, Excel will read the input for the sine function as radians. So what we need to do is convert our inputs of degrees into radians. To do that, I've created another column that I will use to convert my degrees values into radians. So this will be the refracted angle in radians. First, I want to type an equal sign to tell Excel that I'm going to use a function. Then I want to click on the cell for the degree value that I want to convert. That'll put C2, the cell that I'm converting. Then I want to do times. I want to type pi. After pi, I have to use the open and close parentheses, and then divided by 180. Okay, so that'll convert my 40-degree refracted angle into a 0.698 radian refracted angle. This completes the task for the first angle, In order to do it for all of the angles, all you have to do is pull down this little square in the lower right corner. So click on that, drag it down to fill in all of your table values, and Excel will automatically convert them all for you. And if you scroll back over those table values, you will see the first one that I input was C2, and then I converted from degrees to radians using this formula. If I go down one, then the second refracted radian angle will use the value for C3. So cell C3 is the second degrees refracted angle. The next one will be C4 down here, and etc. I can also use this pull down the square trick for the incident angles, but just to be careful, I'm going to type in the first value. So D2 is the first incident angle in degrees value that I want to use. I'm going to multiply by the pi function and then divide by 180. Hit enter, and that gives you the incident angle in radians. I then drag down the square in the lower right corner to fill in my entire table, and it gives me that. Okay, now that we have our angles in radians, I want to take the sine of those angles. This is easy to do in Excel. I type equals to tell Excel that I'm going to use a function. Then I type sine, open parentheses, click on the cell that you want to take the sine of, close parentheses, and hit enter. So then we have the sine of the refracted angle. Drag down the square to fill in the table, and we get these values. Finally, I want to do the same thing for the incident angles, so I type equals sine, open parentheses, G2 is my column for the incident radian angles, close parentheses, enter, and then drag down. Notice that when I manually did the calculation back on the data table page, I found that the sine of 39 degrees was 0.63. Just to check to see if we're on the right track, I can see that if I have an input for a refracted angle of 39 degrees, then my output will be 0.63. Now I want to make a chart from these values, so I'll highlight both columns of the sine of the angles. I will go to Insert, Recommended Charts, and the scatter plot is good. So I'll hit OK there. Okay, once I have the data in chart form, I'm going to want to add a trend line. So I'll hover over one of the data points, right-click, Add Trend Line. Give it a second and it'll come up. Excel will draw a best fit straight trend line. I do want to use linear for this. And if I scroll to the bottom of the Format Trend Line settings, I want to display equation on chart, and I'll get an equation that looks like this. The equation will have the form of y equals mx plus b. If I had better data, hopefully that b value will be close to 0 for you guys. So then the y equals mx part is going to be the important part. And now let's think about why this equation is actually useful to us. So I'm going to go back to here so I can write. Now what I'm plotting and what I get from that chart is a formula y is equal to mx. The y values are the sines of the incident angles, and the x values are the sine of the reflected angles. Okay, I want to compare this to Snell's law, where I have n for the incident material times the sine of the incident angle equals n for the refracted material times the sine of the refracted angle. In this case, the incident material is air, so Ni will just be 1. Okay, that leaves me with sine incident angle equals N refracted times sine refracted. If I compare this to the y equals mx equation that I just looked at, I can see that I'll have sine theta I equals m times sine theta r. Okay, so a direct comparison tells us that the slope m will be the same as the incident of refraction for the refracted material. You will have to do this 2 times. You have to make 2 separate graphs. One will be for trial 1, and the other one will be for trial 2. Okay, so your sine theta r values will change for trial 1 and trial 2. This will give you 2 values of nr, and you're going to want to eventually take an average of these 2. First, though, we have some more questions to answer. So question 9 just asks if the graph is consistent. Explain that. For question 10, you want to use those best fit line slopes. This is where you take the average and you'll calculate a percent error with your value for the index of refraction for the plastic. After that, you have a couple more questions for part 2, and then you move on to part 3. The setup for part 3 is very similar to what we used in part 2. The big difference is that we have changed the direction of the piece of plastic. So you'll have a ray coming from the light source. It will first pass into the curved side, and then it will refract out into the air. We also added a viewing screen, which you'll see in the video. But here's the idea with part 3. You have an incident ray that first passes directly into the plastic on the curved side. Because it's entering that plastic straight on, there will be no refraction at this part. When the light ray gets to the back side of the curved prism, there will be refraction into the air. So the ray will refract right here. So you have an angle of incidence that you measure right here for when the ray hits the back of the prism, and you have an angle of refraction that you measure right here. Now the different colors of light actually refract at slightly different angles. So at some point, you'll see the colors of light start to spread out as they refract. And you'll see a rainbow coming out the back end of the prism. We talked about this when we learned about rainbows back in lecture. And then also, for this part, we have total internal reflection. So for this part, it'll have to be at a steeper angle. But you'll have an incoming ray that'll hit the center of the back of the prism, and instead of refracting into the air, it will totally reflect and come out the front of the prism. Scrolling down, you'll see some questions that you'll have to answer as you watch the video. Let's actually switch back to the video and check that out. Okay, so this is where the dispersion and total internal reflection part starts. You can see the setup's the same. Here you have the incident ray coming in from the bottom. The refracted ray is coming out the top. You can see that as the disk rotates, the light will start to become a rainbow. You can see this on the viewing screen in the back. So you'll have to answer questions 14, 15, and 16 as you watch the video. For question 17, you can basically pause the video. Well, you can pause it at any point, but at one point in the video, we zoom in on the colors. Okay, and so this gives you a more clear view of what the angles of refraction actually are. You can see that red here refracts at about, I would say, 76.5 degrees, and then blue and violet to the right are closer to 80. So you'll use those angles of refraction in Snell's law right here. And then you can use that to calculate the different indices of refraction for the red and the blue light. You don't have to make a chart for this part. And then finally you have total internal reflection. Let's go back to the video for that. If I fast forward a little bit. Okay, when I spin the disk a little bit further, you'll see that the incident angle right here starts to increase, and when that angle passes the critical angle, you'll get total internal reflection. And you can also see this on the disk itself. So let me go back here. If you look on the disk, you can see there's still a refracted ray right here in the upper part of the disk. If I step forward just a little bit, when that disk rotates a little bit more, that refracted ray is going to disappear completely. Okay, a little bit more. Okay, and right there is when the refracted ray disappears. And instead of a refraction, you have the incoming ray going into the plastic, and it's reflecting off the back of the prism. Right, so that's pretty cool. You have an incident ray that passes into a material, and then it seemingly reflects off of nothing, right? Just thin air in the back. But it's actually happening because of refraction and reflection. Okay, and then back on the lab packet, I'll just scroll down. No, thank you. I'll scroll down. You have a couple more questions to answer, some calculations to do, and that's all for today. So good luck with it. Hopefully you find it interesting, and let me know if you have any questions.